Please subscribe to support the channel. The James Webb Space Telescope has shaken the scientific community in ways that few expected. For decades, cosmologists felt confident that they had a reasonably firm grasp of the origins of the universe. The prevailing model, the Big Bang theory, wasn't just widely accepted. It was deeply entrenched in the scientific worldview, shaping the way textbooks, research, and even popular media explained our cosmic beginnings. Yet, the moment JWST started sending back its earliest images, something extraordinary happened. What scientists expected to see was not what they found. Instead of confirming the neat and orderly predictions of Big Bang cosmology, Webb delivered a reality that appeared messier, stranger, and in many ways, deeply contradictory to what had long been believed. This is where the intrigue lies, the possibility that the universe is far more mysterious than we ever imagined. The James Webb Telescope was designed to peer into the earliest epochs of time, to glimpse the very first galaxies that emerged out of the cosmic dark ages. What it revealed, however, were galaxies that appeared far too massive, too mature, and too organized to exist so soon after the supposed beginning of everything. These findings didn't just raise an eyebrow, they struck at the very foundation of the Big Bang framework. To say this shook cosmology would be an understatement. It left scientists with a profound question. If the universe doesn't behave as predicted, does that mean the model we've trusted for nearly a century could be wrong? This is why the discoveries of JWST are not merely scientific curiosities, they are paradigm-shattering revelations. The telescope has forced experts, students, and even casual followers of science to reconsider what they thought they knew. Are we on the verge of rewriting cosmic history? Could we be standing at the threshold of a scientific revolution as profound as when humanity first realized the Earth revolved around the Sun? These are not idle speculations. These are the real questions echoing across astrophysics departments worldwide today. James Webb has uncovered something so unexpected, so shocking, that it threatens to rewrite the story of the universe itself. Whether or not the Big Bang survives these challenges, one thing is clear: the age of certainty in cosmology is over, and a new era of discovery has begun. The Big Bang theory has long stood as the cornerstone of modern cosmology, the grand narrative that attempts to explain how everything we see around us, galaxies, stars, planets, and even life itself, came to be. At its core, the Big Bang posits that the universe as we know it began around 13.8 billion years ago, not as a vast expanse, but as a singular point of incomprehensible density and temperature. In that instant, all the energy, space, and time of the cosmos emerged and began to expand outward. This wasn't an explosion in the conventional sense. There was no blast into pre-existing space. Instead, space itself expanded. That subtle but crucial distinction is what makes the Big Bang unique. It wasn't matter flying into a void, it was the void itself stretching, dragging matter and energy along with it. In the earliest fractions of a second, the universe was unimaginably hot and dense, filled with a primordial soup of particles. Physicists call this the Planck epoch, a time so extreme that the known laws of physics break down, and our mathematical models can't yet penetrate it. As the universe expanded, it cooled. Within microseconds, quarks and gluons condensed into protons and neutrons. Within minutes, the first atomic nuclei began to form, a process known as Big Bang nucleosynthesis. Hydrogen and helium emerged as the dominant elements, with trace amounts of lithium. These simple elements would later serve as the raw ingredients for stars and galaxies. But at this stage, the universe was still a hot plasma, opaque to light. Photons were constantly scattered by free electrons, making the cosmos look more like a dense fog than the transparent starry sky we see today. It wasn't until roughly 380,000 years later that a monumental event occurred: recombination. Electrons finally paired with protons to form neutral atoms, allowing photons to travel freely for the first time. This first light is what we now observe as the cosmic microwave background, CMB, a faint glow that fills the universe and serves as a fossil imprint of the Big Bang. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB became one of the most compelling pieces of evidence that the universe indeed began with a hot, dense origin. From there, structure began to take shape. Tiny quantum fluctuations in the fabric of space-time, amplified during the period of cosmic inflation, a brief but rapid expansion that occurred in the first sliver of a second, became the seeds of galaxies. Gravity began pulling matter into clumps, leading to the first stars, galaxies, and eventually galaxy clusters. Over billions of years, this process sculpted the vast cosmic web that astronomers map today, a network of filaments and voids stretching across unimaginable scales. The Big Bang model is supported by multiple lines of evidence. The expansion of the universe, first discovered by Edwin Hubble in 1929, is one of the most crucial. When Hubble observed distant galaxies, he found that their light was redshifted, meaning they were moving away from us. The farther away they were, the faster they receded. This relationship, known as Hubble's law, implied that space itself was expanding, a cornerstone of Big Bang cosmology. Another line of evidence comes from the relative abundance of light elements. Predictions made by Big Bang nucleosynthesis match remarkably well with what astronomers actually measure in ancient stars and interstellar gas clouds. This consistency strengthens the case for a hot, dense origin. Then, of course, there is the cosmic microwave background, the thermal echo of the Big Bang, which has been mapped in exquisite detail by satellites such as COBE, WMAP, and Planck. These observations reveal not only the temperature of the CMB but also its tiny fluctuations, which correspond to the seeds of cosmic structure. The precision of these measurements has allowed cosmologists to pin down the age of the universe, 13.8 billion years, with remarkable confidence. For decades, the Big Bang theory has not just explained the origin of the universe but has also provided a framework to predict its future. Depending on the density of matter and the mysterious force of dark energy, the universe could continue expanding forever, slow down, or even reverse into a big crunch. The current consensus, bolstered by the discovery of accelerating expansion in the late 1990s, suggests that dark energy dominates, and the cosmos will expand indefinitely, growing colder and emptier with time. And yet, despite its success, the Big Bang has always had mysteries lurking in the background. Questions about the true nature of dark matter and dark energy, the physics of inflation, and the conditions at the very first instant remain unresolved. For a long time, cosmologists were comfortable with these unknowns, believing that new observations would gradually fill in the gaps without overturning the model. But this is where the James Webb Space Telescope enters the picture. Built with the specific purpose of probing the earliest epochs of the universe, JWST was expected to showcase the Big Bang's predictions in stunning clarity. Astronomers thought it would reveal small, primitive galaxies, still in the process of forming, confirming the narrative of gradual cosmic evolution. Instead, it delivered a cosmic twist, finding galaxies that shouldn't exist according to the Big Bang timeline. This is where the tension begins. The Big Bang provides a story of slow, orderly development. The universe starts simple and gradually becomes complex. Yet Webb's revelations suggest that complexity appeared almost immediately, far earlier than expected. If the Big Bang is correct, how could such massive, organized galaxies appear within just a few 100 million years? When the Big Bang theory became the standard model of cosmology, it did more than simply tell a story about the universe's beginning. It laid out a timeline of how cosmic evolution should unfold. This timeline gave astronomers clear expectations about what they should see when they looked deep into space, and therefore, far back in time. If the universe really began 13.8 billion years ago and followed the developmental path outlined by the Big Bang framework, then the earliest epochs would be filled with small, faint, and unstructured galaxies. These galaxies would be in their infancy, filled with clouds of gas and only just beginning to form their first generations of stars. The idea was that the first few 100 million years after the Big Bang, sometimes called the cosmic dawn, were a kind of cosmic nursery. Stars would ignite for the first time, lighting up the universe after its long dark ages, but they would do so in clumps that were messy, irregular, and far smaller than the vast spiral or elliptical galaxies we see around us today. Scientists imagined them as chaotic building blocks, constantly colliding and merging, gradually forming larger structures over billions of years. This expectation was based on decades of theoretical work and computer simulations. Cosmologists had modeled how gas clouds, influenced by gravity and the scaffolding of dark matter, would collapse and form stars. These simulations suggested a slow process. Small halos of matter would form first, and only after many mergers and billions of years would giant, mature galaxies appear. In this model, looking deeper into space was like peering back into a baby photo album of the cosmos. The images would show the universe in its awkward childhood, galaxies still stumbling into existence. The Hubble Space Telescope had already pushed humanity's vision far into the early universe. Its famous ultra-deep field revealed thousands of galaxies at different stages of evolution, stretching back billions of years. But Hubble was limited by its wavelength sensitivity. It could only peer so far into the infrared, which is crucial for studying the earliest galaxies. Light from the most ancient galaxies has been stretched, or redshifted, by the expansion of the universe into infrared wavelengths invisible to Hubble. That's why the James Webb Space Telescope was designed as a primarily infrared observatory. To finish what Hubble had started, to lift the veil on the very first generation of galaxies. The picture painted by theory was simple and elegant. JWST would open its golden mirror, aim deep into patches of empty sky, and find small, faint smudges of light, the earliest galaxies. These would be irregular in shape, poorly organized, and relatively dim compared to the more majestic galaxies we see today. They were expected to resemble mere fragments of what would later become the grand spirals and ellipticals. For astronomers, this was the anticipated confirmation of a beautiful timeline. First stars, then small galaxies, then larger galaxies, then galaxy clusters, leading ultimately to the universe we inhabit today. In fact, many researchers hoped JWST would not so much surprise them as reinforce the Big Bang narrative with greater clarity. They wanted to measure the rate of star formation in these young galaxies, to map the stages of growth, and to refine the details of the existing model. The expectation was not that the telescope would overturn the standard cosmology, but that it would provide more precision to a story already believed to be mostly correct. In other words, Webb was supposed to be the universe's historian, filling in the missing chapters of a book whose ending was already assumed. But the universe, as it turns out, had other plans. When the first data came in, astronomers did indeed see galaxies from incredibly early times, some less than 500 million years after the Big Bang. Yet these galaxies did not look like the faint, chaotic building blocks they had anticipated. Instead, they appeared mature, massive, and astonishingly well-structured, as if billions of years of cosmic evolution had been condensed into a cosmic blink of an eye. That stark difference between expectation and reality is precisely what threw cosmology into turmoil. What scientists thought would be baby pictures of the universe turned out to be snapshots of unexpectedly mature entities, galaxies that by all rights should not exist so soon after the beginning. And this is where the James Webb Space Telescope's role becomes pivotal, because the very design of this observatory made it uniquely suited to uncovering such cosmic surprises. The James Webb Space Telescope was never meant to be just another observatory. It was envisioned as the successor to Hubble, designed to push humanity's cosmic vision further than ever before. For decades, Hubble had served as our window to the universe, revolutionizing our understanding with its deep field images and stunning views of galaxies, nebulae, and distant supernovae. But even Hubble had limits. Its instruments were primarily tuned to visible and ultraviolet light, which meant that it struggled to capture the faint, stretched-out glow of the earliest galaxies. The expansion of the universe had shifted their light into the infrared, well beyond Hubble's capabilities. That gap in our vision was precisely why Webb was created. Webb was built to be an infrared powerhouse. Every part of its design reflects that mission. Its massive 6.5-meter segmented mirror, coated in gold to optimize infrared reflection, dwarfs Hubble's 2.4-meter mirror. Its instruments are carefully shielded by a tennis court-sized sunshield that blocks heat from the sun, Earth, and Moon, keeping the telescope cold enough to detect faint infrared signals from billions of light-years away. Its detectors are so sensitive that they can register the heat signature of a bumblebee at the distance of the Moon. And unlike Hubble, which orbits relatively close to Earth, Webb was sent 1 million miles away to a gravitationally stable point called L2, where it can stare into the darkness of space without interference. The entire mission was shaped around one goal: to look further back in time than any telescope before it. Because of the finite speed of light, peering into deep space is also a journey into deep time. When Webb captures light from a galaxy billions of light-years away, it is not seeing that galaxy as it is today, but as it was when the light first left it. This allows astronomers to directly observe the past, to witness galaxies forming in the early universe. With Webb, scientists expected to reach as close as 200 to 300 million years after the Big Bang, into the era when the first galaxies and stars ignited. To put this into perspective, if the universe's history were compressed into a single calendar year, Hubble had shown us what the cosmos looked like around early February. Webb, on the other hand, was designed to reveal what happened in the first week of January, the very beginning of the story. This is why the telescope's launch in December 2021 was surrounded by such anticipation and anxiety. Engineers knew the mission had to succeed flawlessly. Its deployment involved hundreds of moving parts and complex maneuvers, each of which had to work perfectly or risk mission failure. For decades, scientists had pinned their hopes of solving the mysteries of the early universe on this one observatory. When Webb unfolded in space and cooled to its operating temperature, it was like opening a time machine. For the first time, humanity had the ability to probe the epoch of the cosmic dawn, the period when the first galaxies assembled, the first stars burned, and the first heavy elements began to form. Astronomers eagerly anticipated faint, irregular galaxies flickering into view, their chaotic forms marking the tentative beginnings of cosmic structure. This was the role JWST was designed to play, the ultimate storyteller of the universe's youth, the telescope that would confirm the Big Bang's predictions and fill in the missing pieces of our cosmic timeline. But as the images began to stream back, the story took an unexpected turn. Instead of the messy, fragile-looking galaxies scientists thought they would find, Webb revealed mature, luminous structures that seemed far too advanced for their age. These were galaxies shining brightly at redshifts that correspond to times when, according to the Big Bang model, the universe should have been in its infancy. Webb was not just showing us the first galaxies, it was showing us galaxies that defied the very expectations it had been built to test. This shock, perhaps more than anything else, illustrates why Webb has become such a disruptive force in cosmology. The telescope was designed to refine our understanding of the Big Bang, but it ended up raising questions that strike at the heart of the model itself. And nowhere was this more apparent than in the very first images Webb delivered, which stunned even the most seasoned astronomers. The first images from the James Webb Space Telescope were nothing short of revolutionary. Scientists had been prepared for faint, irregular smudges, the cosmic equivalent of infant scribbles, tiny, chaotic galaxies just starting to take shape in the early universe. What they actually received, however, was a cosmic shockwave in visual form. Galaxies that appeared far too massive, far too luminous, and astonishingly well-structured to exist so soon after the Big Bang. These images didn't just extend our cosmic view, they shattered the narrative that cosmologists had spent decades constructing. One of the most striking discoveries was the presence of galaxies that exhibited spiral and elliptical shapes, forms that were thought to require billions of years of evolution to develop. In conventional Big Bang cosmology, the first few 100 million years after the universe's birth should have been a chaotic period. Gas clouds collapsed under gravity, merging and interacting violently to form small clumps of stars. These early galaxies were expected to be disorganized, irregular, and relatively dim, just beginning to coalesce into the larger structures that dominate the modern cosmos. Yet Webb's images showed otherwise. For instance, in some fields, JWST captured galaxies that were not only larger than expected but also densely populated with stars, shining with a brightness that implied extraordinarily high rates of star formation. These galaxies appeared as fully developed entities rather than the embryonic star clusters predicted by standard models. Their size and organization suggested that they had undergone significant growth and star formation in a fraction of the time that the Big Bang timeline allows. Essentially, these galaxies were already mature when the universe was still just a toddler by cosmic standards. Even more astonishing were observations of galaxies existing less than 500 million years after the Big Bang. According to traditional cosmology, the universe at this age should have contained mostly small proto-galaxies, gradually merging over billions of years into the larger structures we see today. Webb, however, revealed galaxies with stellar masses comparable to those found in the modern universe, suggesting that these structures had formed, and formed quickly. The universe was, in a sense, ahead of schedule. These findings were not subtle discrepancies, they were profound contradictions. In addition to size and brightness, the spectra captured by JWST hinted at surprisingly mature chemical compositions. Some of these early galaxies contained higher proportions of heavier elements than expected, implying that multiple generations of stars had already lived and died, enriching the interstellar medium. This is particularly baffling because forming such elements requires a timescale much longer than the models allowed. The presence of these metals suggested that star formation and galactic evolution had proceeded at a pace that current theories cannot easily explain. Astronomers around the world were stunned. Early press releases and academic presentations describe the galaxies as unexpected, mature, or even impossible in some cases. Social media and preprint servers lit up with debates about whether these findings were genuine, whether the distance measurements could be wrong, or whether some unknown observational bias was at play. Yet repeated measurements confirmed the redshifts, indicating that these galaxies were indeed forming far earlier than expected. What makes this discovery so disruptive is that it directly challenges the narrative of gradual, stepwise formation embedded in Big Bang cosmology. Instead of a universe where small galaxies slowly merged into larger ones over billions of years, Webb's images suggest a universe capable of forming complex, organized galaxies astonishingly quickly. The images show that the cosmos may have been far more efficient at creating massive structures than previously imagined, raising fundamental questions about the physics underlying galaxy formation. The shockwave caused by these first images cannot be overstated. Scientists who had spent their careers modeling early cosmic evolution were suddenly confronted with a universe that refused to obey their predictions. It was as if someone had handed historians photographs of fully developed cities from the earliest days of civilization, forcing a complete reassessment of the timeline. The Big Bang's predictions about the infancy of galaxies were being called into question in the most direct, visual way possible. And yet, this isn't just about aesthetic beauty or surprise. The implications are profound. If galaxies can mature this quickly, it suggests that our understanding of how matter coalesces, how stars form, and how dark matter scaffolds the universe may need significant revision. The first images from JWST are not mere pictures. They are empirical evidence that the universe is far stranger and more efficient than we ever imagined. This brings us directly to a central problem. According to the standard Big Bang model, the universe shouldn't have had enough time for galaxies to grow this large and organized. It forces cosmologists to confront uncomfortable questions about the timing and mechanics of cosmic evolution, and whether our theoretical frameworks need fundamental adjustments. The tension between observation and expectation is now undeniable, setting the stage for deeper mysteries about the size, formation, and evolution of early galaxies. The problem revealed by the James Webb Space Telescope's first images is not merely one of surprise or aesthetic discrepancy. It strikes at the very mechanics and timelines predicted by Big Bang cosmology. According to the standard model, the growth of galaxies is an inherently gradual process. After the initial expansion of the universe from the Big Bang, matter began to coalesce under gravity, forming small clumps of gas and dark matter halos. These proto-galaxies then merged, collided, and accreted more material over hundreds of millions, eventually billions, of years. This hierarchical buildup of structure is a cornerstone of cosmological theory, supported by extensive computer simulations that trace the evolution of the universe from its earliest moments to the present day. In this framework, fully mature galaxies, those that are massive, organized, and chemically enriched, should not exist in the first few 100 million years after the Big Bang. The early universe, in this model, is a messy, turbulent environment. Star formation is slow, gravitational interactions are chaotic, and the buildup of metals through supernovae requires multiple generations of stars. The images from JWST, however, show galaxies that appear fully formed, with large stellar masses and well-defined structures, at times when the universe was barely 500 million years old. This is a tiny fraction of the 13.8 billion years of cosmic history, roughly equivalent to seeing a fully grown adult in a human timeline at the age of infancy. The discrepancy becomes even more pronounced when considering the time needed for stars to synthesize heavier elements. Heavier elements, carbon, oxygen, nitrogen, and so on, are produced within stars and released into the interstellar medium when those stars die. In the Big Bang framework, only the lightest elements, hydrogen, helium, and traces of lithium, existed immediately after the universe began. The complex chemical signatures observed in some of Webb's early galaxies imply that multiple cycles of star formation and death had already occurred. Simply put, these galaxies appear chemically mature, which is impossible under the expected timescales for early cosmic evolution. The growth of structure is not just about star formation. Gravity-driven accretion, galactic mergers, and the assembly of dark matter halos are all slow processes. Even under the most optimistic models, the formation of a massive, organized galaxy is expected to take at least 1 to 2 billion years. Webb's observations, however, place such galaxies at less than 500 million years after the Big Bang. This means that galaxies in the early universe are forming, organizing, and producing stars at a rate orders of magnitude faster than theory predicts. Another aspect that makes this so problematic is the size of the galaxies. Not only are these galaxies mature, but they are also enormous in terms of stellar mass. According to current simulations, early galaxies should be small, compact, chaotic, and gradually merging with neighboring structures to build more massive systems. Yet JWST has revealed galaxies that already rival or exceed the mass of the Milky Way, implying that the process of mass accumulation has been extraordinarily efficient. Such rapid growth is difficult to reconcile with existing models that incorporate the known physics of dark matter, gas cooling, and star formation. Even the timeline for the cosmic dawn, the epoch when the first stars and galaxies reionized the universe, is called into question. If massive, mature galaxies already exist at such early times, it implies that the universe may have undergone reionization earlier and faster than predicted. This, in turn, complicates our understanding of how radiation and ionization progressed through the intergalactic medium, adding yet another layer of tension between observation and theory. The implications extend beyond early galaxies themselves. The very structure of the universe as simulated by cosmologists depends on the idea that galaxies gradually form within a network of dark matter, following a predictable hierarchical pattern. If galaxies can bypass this slow growth and appear mature so quickly, it challenges the assumptions about the interplay between visible matter and the dark matter scaffolding thought to guide galaxy formation. It suggests that the universe may be capable of building complexity far faster and more efficiently than our current laws of physics, as applied on cosmic scales, would allow. In short, this isn't a minor discrepancy, it's a fundamental challenge to the Big Bang timeline. The expectation that structure grows slowly over billions of years is embedded deeply in cosmological theory, supported by countless simulations and observational inferences. Webb's findings, showing galaxies that are already large, organized, and chemically enriched within the first few 100 million years, imply that either the processes governing galaxy formation are drastically different from what we understand, or our assumptions about the early universe itself need re-evaluation. This fundamental tension naturally leads into the next question: the mystery of galaxy size in the early universe. The massive scale of these early galaxies, combined with their unexpected maturity, is not only shocking but also deeply puzzling, because it defies the growth curves predicted by the standard cosmological model. The story of how galaxies achieve their size and organization so rapidly is where the next layer of the Webb discoveries becomes even more astonishing. What makes the James Webb Space Telescope's discoveries truly extraordinary is the scale of the galaxies it has revealed in the early universe. Less than 500 million years after the Big Bang, essentially the cosmic equivalent of infancy, JWST has identified galaxies that are not just present but massive, luminous, and astonishingly well-structured. This is a puzzle that cosmologists are still grappling with because, according to existing models, such galaxies simply should not exist at this epoch. The standard model of galaxy formation, grounded in the framework of hierarchical structure growth, predicts that early galaxies start small and gradually merge to build larger structures. These first galaxies are expected to be compact, clumpy, and irregular, with relatively low stellar masses. Only after billions of years of star formation, mergers, and accretion of gas and dark matter should galaxies reach the massive sizes we see in the contemporary universe. Yet Webb has captured galaxies whose stellar masses rival or exceed that of the Milky Way, an enormous spiral galaxy in our cosmic backyard, at a fraction of the expected age. The implications of these observations are staggering. To reach such sizes so quickly, galaxies would have needed to form stars at an extraordinarily high rate while simultaneously accumulating vast amounts of gas and dark matter. This accelerated growth conflicts with our current understanding of the physics of star formation, which involves processes like gas cooling, feedback from supernovae, and the gravitational influence of dark matter halos. According to simulations, all of these factors should act as brakes on the rapid buildup of mass. Yet Webb's observations suggest that these brakes were somehow overridden in the early universe. Some of the galaxies Webb has detected are not just massive, they are surprisingly organized. They exhibit clear structures, with coherent shapes and dense stellar populations, implying that they underwent a complex formation process in record time. For cosmologists, this is akin to finding a fully furnished house already standing in a city that was supposed to be under construction. The rapid emergence of such massive, structured galaxies raises profound questions about how matter coalesces in the early universe. The size problem becomes even more evident when considering the distribution of these early massive galaxies. Multiple independent surveys with Webb have identified them across different regions of the sky, indicating that these objects are not anomalies or flukes. Their widespread presence suggests that rapid, large-scale galaxy formation was a common feature of the early universe, not a rare event. This challenges the conventional simulations that model galaxy formation under Big Bang assumptions, which struggle to produce anything of comparable mass so early in cosmic history. One of the ways astronomers quantify this problem is through stellar mass functions, which predict the number of galaxies of a given mass at various points in cosmic time. Observational data from Webb consistently show an overabundance of massive galaxies at high redshifts compared to these predictions. The discrepancy is not small. In some cases, the number of massive galaxies detected exceeds theoretical expectations by an order of magnitude. This mismatch forces cosmologists to question the very assumptions underlying galaxy formation models, from the efficiency of star formation to the behavior of dark matter in the early universe. Moreover, the sheer size of these galaxies raises questions about the timeline of cosmic evolution. In standard Big Bang cosmology, the universe at 500 million years post-Big Bang was still in the early stages of reionization, a period when the first stars and galaxies began ionizing the neutral hydrogen that filled intergalactic space. The discovery of such massive galaxies implies that the processes leading to reionization were already well underway, or perhaps even largely completed, much earlier than previously believed. This contradicts earlier models of the cosmic timeline and suggests that the first few hundred million years of the universe were far more dynamic and productive than expected. The size and maturity of these early galaxies have profound implications not only for our understanding of star formation and galactic evolution, but also for the broader cosmological model. If massive galaxies can form so quickly, it could indicate that some fundamental aspects of the physics underlying galaxy formation, such as gas accretion rates, star formation efficiencies, or the role of dark matter, are not yet fully understood. Some theorists even suggest that this might point to entirely new physics, mechanisms that would allow the early universe to build structure at rates far exceeding current predictions. In short, the galaxy size mystery is not just about numbers or shapes. It is a fundamental challenge to the narrative of the universe's growth. Massive, mature galaxies existing less than 500 million years after the Big Bang force cosmologists to reconsider long-held assumptions about how galaxies form, grow, and interact. They confront us with a universe that seems far more efficient and ambitious in its structure building than our theories anticipated. This mystery also links directly to another equally startling discovery: the rate at which stars were forming in these early galaxies. The sheer mass of these systems implies incredibly high star formation rates, which challenges the timelines established by traditional cosmology and adds yet another layer to the growing tension between observation and theory. One of the most startling revelations from the James Webb Space Telescope is not just the size of early galaxies but the intensity at which they are forming stars. Star formation rates in the early universe, as revealed by Webb, are far higher than cosmologists ever anticipated, and this finding challenges long-standing assumptions about the pace of cosmic evolution. In the conventional Big Bang framework, the first galaxies were expected to build their stellar populations slowly and incrementally. Stars formed in bursts over hundreds of millions of years, gradually accumulating enough mass to create the massive, organized galaxies we see in the modern universe. Webb, however, is showing that this process may have been extraordinarily accelerated. JWST's infrared instruments have allowed astronomers to detect the light from stars that formed billions of years ago, when the universe was still in its infancy. By analyzing the spectra of these early galaxies, researchers can infer not only their stellar masses but also the rate at which stars are being born. The results are astonishing. Some galaxies less than 500 million years after the Big Bang appear to be forming stars at rates hundreds of times faster than those seen in nearby galaxies today. For perspective, the Milky Way produces roughly 1 to 2 solar masses of stars per year. Webb has identified galaxies churning out hundreds or even thousands of solar masses annually at epochs when the universe was barely a toddler. This discrepancy forces a reconsideration of the physics governing star formation. In theory, there are natural limits on how quickly gas clouds can collapse under gravity and ignite nuclear fusion. Feedback processes, such as supernova explosions, stellar winds, and radiation pressure, typically act as brakes, preventing galaxies from forming stars too rapidly. Yet in Webb's early observations, these breaks seem to have been either absent or dramatically less effective than predicted. The galaxies observed are simultaneously massive, mature, and highly efficient at producing stars, suggesting that the conditions in the early universe allowed for a level of stellar productivity that standard models cannot easily accommodate. The implications of these elevated star formation rates extend beyond individual galaxies. High rates of star formation imply that the early universe could have produced a substantial amount of ionizing radiation much earlier than expected, impacting the timing and progression of cosmic reionization. In the traditional picture, reionization, the process in which neutral hydrogen atoms were ionized by the first stars and galaxies, was thought to have occurred gradually over hundreds of millions of years. But if galaxies were forming stars at this unprecedented pace, reionization may have proceeded far more rapidly, potentially reshaping our understanding of the universe's first billion years. JWST has also revealed that these star formation rates are not isolated to a few unusual objects. Surveys of multiple early universe fields show that highly productive galaxies are surprisingly common, suggesting that rapid star formation was a widespread feature of the infant cosmos rather than a rare anomaly. This universality exacerbates the problem for cosmologists because it cannot be easily dismissed as a statistical fluke or observational bias. The universe seems to have been extraordinarily adept at building stars almost immediately, contradicting models that predict a slow and steady accumulation of stellar mass. The combination of massive galaxies and extreme star formation rates creates a profound tension with the existing theoretical framework. Computer simulations of galaxy formation, which incorporate known physics, struggle to reproduce objects of such mass and productivity at these early times. These simulations rely on the interplay between gravity, gas dynamics, and dark matter to explain how matter collapses into stars and galaxies. Webb's findings suggest that either the simulations are missing critical aspects of early cosmic physics, or our understanding of the timeline of the universe's evolution is fundamentally flawed. Some theorists have proposed mechanisms to explain these accelerated star formation rates. These include more efficient gas cooling processes, the presence of unusually dense dark matter halos, or alternative initial conditions in the early universe that allowed rapid accumulation of matter. Others suggest that perhaps unknown processes, possibly exotic physics beyond the standard model, could have driven such extreme early growth. Whatever the explanation, it is clear that the conventional picture of slow, stepwise evolution does not match what Webb is showing us. These unexpectedly high star formation rates also tie directly to the impossible galaxies debate. If galaxies are forming stars at such extraordinary speeds, then their rapid maturity is less of a surprise, but still deeply problematic. The term impossible arises not because these galaxies violate any laws of physics outright, but because they are impossible to reconcile with the timescales and processes predicted by standard cosmology. In essence, Webb has revealed a universe that grows up incredibly fast, far faster than our current theories allow. Moreover, the high star formation rates exacerbate other cosmological tensions. They suggest that the early universe was more dynamic, more energetic, and perhaps even more complex than previously understood. Combined with the observed size and maturity of early galaxies, this evidence challenges the Big Bang model's timeline, indicating that the universe's first few 100 million years were not a slow crawl toward structure, but a period of explosive growth and organization. In short, JWST's observations of star formation rates are rewriting our expectations about how quickly galaxies can form stars, how rapidly chemical elements can be produced, and how early cosmic evolution proceeded. The universe, it seems, is capable of assembling large, complex, and luminous structures with breathtaking speed, forcing cosmologists to reconsider the assumptions that underpin the Big Bang framework. This revelation naturally sets the stage for the heated debate among scientists about the nature of these impossible galaxies, which appear to challenge not just models of star formation but the very foundations of cosmological theory itself. The James Webb Space Telescope didn't just reveal unexpected galaxies, it sparked an ongoing and intense debate among scientists over what these objects truly represent. Many researchers have begun referring to these early, massive, and highly organized galaxies as impossible galaxies. The term is not meant to suggest that they literally violate the laws of physics, but rather that they are impossible to reconcile with the established expectations of Big Bang cosmology and our current models of cosmic evolution. These galaxies, forming less than 500 million years after the Big Bang and yet already massive and chemically enriched, challenge the fundamental assumptions about how quickly the universe can build complexity. The label impossible first emerged in academic circles as astronomers struggled to fit Webb's observations into simulations of early galaxy formation. Traditional models, based on well-understood physics, predicted that galaxies at such early epochs should be small, faint, and irregular. Hierarchical formation models, the backbone of galaxy evolution theory, suggest that mass accumulates slowly through mergers and accretion over billions of years. The appearance of massive, mature galaxies so early in the universe directly contradicts these predictions, leading some scientists to describe them as borderline unexplainable. The debate is highly charged because it questions the very framework that underpins modern cosmology. If these galaxies truly exist as observed, it suggests that either the physics governing early galaxy formation is incomplete or that the timeline of cosmic evolution is fundamentally miscalculated. Some researchers have proposed that observational errors, misestimated distances, misidentified redshifts, or unusual calibration artifacts might be responsible. After all, claiming the existence of galaxies that shouldn't exist is a bold statement, and extraordinary claims require extraordinary evidence. However, the more Webb data comes in, the harder it becomes to dismiss these galaxies as anomalies. Multiple independent observations, across different fields of view, consistently reveal the presence of these massive early galaxies. Their characteristics, high stellar mass, rapid star formation, organized morphology, appear repeatedly in the data, making it increasingly unlikely that they are the result of observational errors or statistical flukes. The impossible galaxies are, in fact, a reproducible and robust phenomenon. Some astronomers have suggested that these galaxies might not be truly impossible if we adjust the parameters of existing models. For instance, star formation could be far more efficient in the early universe than previously assumed, or gas accretion onto galaxies might have occurred at unusually rapid rates. Even the behavior of dark matter, which acts as the gravitational scaffolding for galaxy formation, might be different in the earliest epochs than current simulations predict. These explanations could, in theory, account for the unexpected maturity of these galaxies without overturning the Big Bang entirely. Yet there are voices in the scientific community pushing the discussion even further. Some cosmologists argue that these galaxies may be evidence of a universe fundamentally different from the one predicted by the Standard Model, a universe capable of assembling complex structures far more rapidly than any current theory allows. These interpretations are provocative because they suggest that our understanding of cosmic beginnings, and perhaps even the mechanics of the universe itself, may be incomplete. The debate is further complicated by the precision and reliability of JWST's instruments. Unlike earlier telescopes, Webb's infrared sensitivity allows for unparalleled clarity in observing distant galaxies. This means the data challenging conventional expectations is unlikely to be an artifact. Scientists must grapple with the reality that what they are seeing is real, yet inexplicably early and advanced. That realization has caused some to openly question whether the Big Bang model, or at least its standard timeline of galaxy formation, is adequate. Another layer of controversy comes from the social dynamics within the scientific community. Established theories like the Big Bang carry immense institutional weight, supported by decades of observations, simulations, and theoretical work. Admitting that these impossible galaxies cannot be reconciled with standard models threatens long-held paradigms, and many researchers are cautious about jumping to radical conclusions. This has sparked vigorous debates at conferences, in preprint archives, and across online scientific forums, as cosmologists wrestle with whether these discoveries represent minor anomalies, gaps in existing models, or evidence that the Big Bang framework itself may need reconsideration. The term impossible also has a rhetorical effect. It captures the public imagination and signals the profound significance of these findings, but it simultaneously reflects the deep unease within the scientific community. These galaxies are impossible not because they break known physics, but because they defy the timelines, efficiencies, and growth patterns predicted by our most trusted models of cosmic evolution. Each new observation adds weight to the tension, suggesting that whatever the explanation, it will require a fundamental rethinking of how we understand the early universe. This debate naturally leads into questions about the role of dark matter in galaxy formation. Since dark matter is thought to provide the gravitational scaffolding essential for building galaxies, understanding whether these impossible galaxies challenge the behavior or influence of dark matter is a crucial next step. If current models of dark matter cannot explain such rapid galactic growth, then the problem extends beyond the galaxies themselves to the fundamental components thought to structure the cosmos. The role of dark matter in galaxy formation is central to the standard cosmological model, and the James Webb Space Telescope's discoveries have made this component more enigmatic than ever. In the Big Bang framework, dark matter acts as the invisible scaffolding upon which galaxies build. It does not emit, absorb, or reflect light, but its gravitational influence is essential. It attracts ordinary, baryonic matter, allowing gas clouds to collapse and form stars. Without dark matter, the universe as we know it, galaxies, clusters, and cosmic structures, would likely never have formed. Cosmologists have long relied on simulations that combine dark matter physics with the behavior of normal matter to predict how galaxies evolve over time. In these models, dark matter halos emerge first, forming a web-like structure across the cosmos. Ordinary matter, drawn by gravity into these halos, slowly cools, condenses, and forms stars. Over billions of years, these small structures merge and accrete additional material, eventually giving rise to the massive, organized galaxies we see today. The process is gradual, regulated by feedback mechanisms such as supernova explosions and radiation pressure, which prevent runaway star formation. JWST's observations, however, challenge this carefully constructed picture. The massive, mature galaxies discovered within the first 500 million years of the universe appear far too advanced to have formed solely within the gravitational wells predicted by standard dark matter models. The rapid growth in stellar mass, combined with the organized structure of these galaxies, implies that the early universe was far more efficient at assembling matter than simulations suggest. In other words, if dark matter alone is guiding the formation of galaxies, it is doing so at a pace and efficiency that current theories cannot account for. One potential issue is that the dark matter halos predicted by simulations may not have grown quickly enough to host the observed galaxies. The halos act as the gravitational framework for baryonic matter, and in standard models, there simply wouldn't have been enough time for them to reach the masses necessary to support such large galaxies. If these halos were insufficient, it raises the question of how these galaxies could have collected and condensed enough gas to form stars so rapidly. The tension is not minor. It calls into question the assumed timeline and dynamics of both visible and invisible matter in the early universe. Some theorists have suggested modifications to the properties of dark matter itself. For instance, alternative dark matter models, such as warm or self-interacting dark matter, could allow for faster halo formation or enhanced clumping of matter in the early universe. Yet even these modifications struggle to fully explain the maturity and mass of the galaxies observed by JWST. The sheer number and distribution of these early, massive galaxies imply a level of organization and growth that is difficult to reconcile with any current dark matter scenario. This complication also extends to star formation. Dark matter halos are supposed to regulate how gas collapses into stars. Feedback processes from supernovae and stellar radiation are expected to slow down star formation in the early universe. The extraordinary star formation rates observed by Webb suggest that either these regulatory processes were somehow suppressed or that the gravitational influence of dark matter acted in unexpected ways. Either scenario requires a re-evaluation of how dark matter interacts with baryonic matter in the earliest stages of galaxy formation. Moreover, these findings have implications for the broader cosmic web. If massive galaxies can form so early, it may mean that the overall structure of the universe, the distribution of galaxies, filaments, and voids, emerged differently than predicted. The very scaffolding thought to shape the cosmos may have operated more efficiently or differently than models suggest, prompting cosmologists to question whether dark matter behaves in ways not yet understood. This, in turn, could have cascading effects on other aspects of the Big Bang model, including the rate of cosmic expansion, the timing of reionization, and the evolution of intergalactic gas. The complications don't stop there. If dark matter explanations fail to account for the rapid formation of massive galaxies, it may suggest that other, as yet unknown processes were at work in the early universe. Some scientists speculate about exotic physics, new forces, variations in fundamental constants, or alternative models of gravity that could have accelerated structure formation. While these ideas are speculative, the impossible early galaxies discovered by Webb make it clear that conventional dark matter alone may be insufficient to explain the early universe's complexity. In essence, JWST has revealed that the universe may have been far more efficient and dynamic in forming galaxies than the standard model predicts. Dark matter, which has been the cornerstone of galaxy formation theory for decades, suddenly seems insufficient to explain the pace and scale of early cosmic evolution. This finding amplifies the tension between observation and theory and forces cosmologists to reconsider some of the most basic assumptions about how structure forms in the universe. This naturally connects to another puzzling aspect of early cosmic evolution, the timing of reionization. If galaxies were forming stars and assembling mass so quickly, the entire narrative of the cosmic dawn and the reionization epoch must be revisited, suggesting a far more complex and accelerated early universe than previously imagined. One of the most profound implications of the James Webb Space Telescope's discoveries lies in the timing and nature of the cosmic dawn, the epoch when the first stars and galaxies ionized the neutral hydrogen that filled the universe. According to the standard model of cosmology, after the Big Bang, the universe went through a period known as the Dark Ages, lasting roughly 400 million years. During this time, the cosmos was filled with neutral hydrogen, making it opaque to high-energy radiation. The first stars and galaxies that formed during this epoch gradually emitted ultraviolet light energetic enough to ionize the surrounding hydrogen, a process called reionization. This phase transformed the universe from an opaque fog into a transparent cosmic web, allowing light to travel freely and shaping the universe as we observe it today. Traditional models suggested that reionization was a slow, patchy process, taking place over hundreds of millions of years, roughly between 400 million and 1 billion years after the Big Bang. Observational constraints from the cosmic microwave background, CMB, and quasar absorption lines provided a general framework for when this reionization could have occurred, and simulations were built around these timelines. It was assumed that the first galaxies would be small, relatively dim, and scattered, producing enough ultraviolet light over time to gradually ionize the universe. Webb's findings, however, challenge this picture in dramatic ways. The massive, mature galaxies that JWST has observed at redshifts corresponding to less than 500 million years after the Big Bang suggest that star formation was already occurring at an intense, accelerated pace. These galaxies are not just forming stars, they are producing vast numbers of high-energy photons capable of ionizing hydrogen. If such galaxies were common, the process of reionization may have begun much earlier and proceeded far more rapidly than previous models predicted. In other words, the cosmic dawn may have arrived sooner and burned brighter than scientists anticipated. This accelerated timeline raises fundamental questions about the pace and mechanics of cosmic reionization. If massive galaxies were widespread and producing enormous quantities of ultraviolet light, it implies that the universe transitioned from opaque to transparent much faster than expected. This conflicts with earlier interpretations of the CMB, which suggested a more extended reionization period. Reconciling Webb's observations with these constraints is proving to be a challenge for cosmologists, requiring either a re-evaluation of the efficiency of early galaxies in producing ionizing radiation or the introduction of new mechanisms that could have accelerated the process. Another aspect that complicates the picture is the chemical maturity of these early galaxies. JWST has detected heavy elements in some of these systems, implying multiple generations of stars had already lived and died. The death of massive stars not only contributes to chemical enrichment but also releases vast amounts of high-energy radiation into the surrounding intergalactic medium. This feedback would accelerate reionization, suggesting that the first billion years of the universe may have been far more active and turbulent than previously thought. The reionization puzzle also affects how we interpret the distribution of galaxies in the early universe. If reionization occurred earlier and more efficiently, then the environment in which subsequent galaxies formed would have been fundamentally altered. The ionized bubbles around early galaxies would have influenced the cooling and collapse of gas in neighboring regions, potentially accelerating structure formation even further. This feedback loop could help explain the presence of massive, mature galaxies so early, but it also complicates the standard narrative and challenges our understanding of cosmic timelines. Webb's data has forced cosmologists to confront uncomfortable possibilities. Either the process of reionization was dramatically faster than anticipated, or the models of galaxy formation and star formation efficiency need to be revised. Some theorists have even suggested that the reionization epoch may have overlapped with periods of unexpectedly rapid galaxy assembly, making the early universe a far more dynamic and complex environment than the traditional Big Bang timeline allows. The implications extend beyond reionization itself. An earlier and faster cosmic dawn could influence measurements of other cosmological parameters, including the Hubble constant, dark matter halo formation rates, and the growth of large-scale structure. If the first stars and galaxies formed and acted so efficiently, it suggests that the universe was capable of organizing matter, producing radiation, and building complexity at a pace that challenges nearly every assumption about the first billion years of cosmic history. Ultimately, the reionization puzzle underscores a recurring theme in Webb's discoveries. The universe is far more efficient, productive, and complex in its early stages than standard models predict. The observations force cosmologists to reconsider not just the timing of key epochs like reionization, but the fundamental physics governing the growth of structure, star formation, and radiation production. The early universe, it seems, is rewriting its own history in ways we are only beginning to understand. This naturally leads into the broader set of responses from scientists trying to make sense of these discrepancies. Some researchers advocate for tweaking existing models to account for accelerated growth, while others suggest more radical revisions to our understanding of the universe's origins. These alternative explanations form the next stage in the ongoing dialogue sparked by JWST's discoveries. In the wake of the James Webb Space Telescope's startling revelations, the scientific community has been grappling with how to interpret galaxies that appear impossibly massive and mature less than 500 million years after the Big Bang. While some headlines emphasize the Big Bang challenge narrative, many astronomers are taking a more measured approach, exploring ways to reconcile Webb's observations with existing cosmological theory rather than abandoning it entirely. These alternative explanations generally involve tweaking the parameters and assumptions in galaxy formation models, aiming to account for the rapid growth of galaxies without discarding the foundational framework of the Big Bang. One of the primary areas under investigation is the efficiency of star formation in the early universe. Standard models typically assume that only a fraction of available gas in a galaxy collapses into stars, with feedback processes, such as supernovae and radiation pressure from young stars, acting as natural regulators that prevent runaway growth. Webb's observations suggest that these feedback mechanisms may have been less restrictive than previously thought, allowing gas to collapse more quickly and stars to form at a prodigious rate. Adjusting these efficiencies in simulations could potentially produce galaxies of the mass and maturity observed, albeit on a timeline that is still faster than originally anticipated. Another potential adjustment involves the inflow of gas from the surrounding intergalactic medium. Traditional models assume that gas accretion onto galaxies is relatively gradual, constrained by the density and temperature of the surrounding environment. However, some theorists propose that the early universe may have contained dense filaments of gas funneled directly into galaxy cores, accelerating their growth. If galaxies could tap into these gas reservoirs efficiently, it would explain how they amassed such significant stellar populations in a fraction of the expected time. This idea does not overturn the Big Bang but suggests that the processes governing matter assembly and star formation are more efficient or more complex than current simulations assume. Cosmologists are also re-examining the role of dark matter in early galaxy formation. While dark matter is already a critical component in hierarchical structure formation, subtle variations in its distribution or interactions could speed up the growth of early halos, effectively providing a stronger gravitational framework for rapid star formation. Some models explore scenarios in which early dark matter halos were denser or more massive than previously estimated, enabling galaxies to accumulate mass and form stars at accelerated rates. Such tweaks maintain the overall structure of the Big Bang framework while offering a potential path to reconcile Webb's data with theory. Chemical evolution models are another area of active research. The presence of heavy elements in early galaxies, detected through JWST's sensitive spectroscopy, suggests multiple generations of stars had already lived and died. Adjusting models to allow for more rapid star formation and faster recycling of stellar material could help explain the surprisingly enriched chemical composition of these galaxies. In essence, scientists are exploring whether the early universe was capable of producing stars and enriching its environment at a pace far beyond what previous simulations suggested. Some astronomers are also considering the impact of initial conditions in the early universe. Slight changes in the distribution of matter, the density of primordial gas, or the timing of cosmic inflation could have created favorable conditions for rapid galaxy growth. These tweaks do not discard the Big Bang itself. Rather, they suggest that the early universe may have had pockets or regions where structure formation was unusually efficient. Incorporating these variations into simulations could help reproduce the types of massive galaxies observed by Webb without invoking entirely new physics. Importantly, these alternative explanations illustrate a fundamental principle of science. When observations challenge a model, the first step is to test whether adjustments to parameters can reconcile theory with data. Many astronomers believe that the Big Bang itself remains robust, supported by overwhelming evidence such as the cosmic microwave background, light element abundances, and the overall expansion of the universe. The impossible galaxies may not invalidate the model. They may instead reveal previously unappreciated nuances in how the early universe formed stars and galaxies. Even within this framework of minor tweaks, however, there is a recognition that these adjustments may have far-reaching consequences. Changing star formation efficiencies, gas inflow rates, or dark matter halo properties in early universe simulations could affect predictions for other cosmological phenomena, including reionization timing, the evolution of galaxy clusters, and the large-scale structure of the universe. In other words, while the Big Bang may not be discarded, the discovery of these galaxies is forcing a reconsideration of how the universe evolved in its first few 100 million years. This measured approach contrasts sharply with the more radical voices in cosmology, who interpret Webb's data as evidence that the standard model may be insufficient to explain the universe's earliest structures. These scientists argue that, rather than simply tweaking existing models, we may need to consider fundamentally new theories that could account for rapid galaxy formation, extreme star formation rates, and the apparent maturity of the first galaxies. The tension between these two approaches, the conservative tweaking of models versus radical reconceptualization, highlights the current crossroads in cosmology. Some researchers are focused on refining simulations and adjusting parameters, seeking incremental solutions, while others view Webb's discoveries as a signal that our understanding of the universe's origin story may need a profound rewrite. Both perspectives stem from the same underlying data, yet they diverge sharply in terms of the philosophical and theoretical implications. This debate naturally opens the door to more radical alternatives to the Big Bang, including theories that propose different origins or cyclical models of the universe. If minor tweaks to galaxy formation are insufficient to reconcile JWST's observations, some scientists argue that we may need to consider entirely new cosmological frameworks, models that challenge the very notion of a single beginning and the slow hierarchical growth of structure. While many astronomers are focused on adjusting existing galaxy formation models, a growing number of voices in cosmology are taking a far more radical stance. For them, the evidence from the James Webb Space Telescope is not merely a challenge to the rate of star formation or the efficiency of early galaxy growth. It is a sign that our understanding of the universe's very origin might be incomplete. These scientists argue that the presence of massive, mature galaxies less than 500 million years after the Big Bang could suggest a universe far stranger than the conventional Big Bang framework allows, one in which the earliest epochs were not a slow, incremental unfolding but a period of accelerated complexity that may point to a fundamentally different cosmological story. Some radical theorists propose that the universe might not have begun in the simple, singular explosion described by the Big Bang model. Instead, they suggest scenarios in which the universe is far older or has undergone multiple cycles of creation and destruction. In these frameworks, the early appearance of massive galaxies is less paradoxical, because the cosmos may have had previous epochs or conditions that allowed complex structures to form rapidly. For example, in cyclic or bouncing universe models, each big bounce provides a new phase of cosmic evolution, potentially carrying over conditions from previous cycles. This could account for the unexpected maturity and abundance of early galaxies observed by JWST. Another radical idea involves questioning the uniformity of the early universe. The standard model assumes that, immediately after the Big Bang, the universe was highly homogeneous and isotropic, with small quantum fluctuations gradually amplified into galaxies and large-scale structures. However, some cosmologists are exploring the possibility that the early universe was far more heterogeneous, with dense pockets of matter forming massive galaxies almost immediately. If these regions existed from the start, the rapid assembly of mature galaxies would be less surprising, but it would fundamentally challenge the assumption of a uniform beginning and suggest a universe with a far more complex initial structure. Other speculative theories explore the nature of dark matter, dark energy, and even fundamental physics itself. If the laws governing the early universe were different, or if unknown forces acted to accelerate the growth of structure, then the emergence of massive galaxies at very high redshifts becomes more plausible. Some researchers are proposing exotic particle physics, modifications to gravity, or interactions between dark matter and baryonic matter that are not captured in current models. While these ideas are still highly speculative, Webb's observations provide a concrete reason to explore them. The early universe appears far more capable of rapid structure formation than previously thought. A particularly provocative suggestion is that the timeline of the universe may not be as linear as commonly believed. In the traditional Big Bang narrative, time unfolds in a smooth progression from the singularity to the present, with cosmic structures gradually forming along this timeline. Some radical models, however, propose that certain structures could form out of sequence, or that cosmic expansion itself may involve phases in which matter and energy behave differently than our current understanding predicts. In these frameworks, impossible galaxies are not anomalies. They are natural outcomes of a universe operating under conditions outside the assumptions of the standard model. These radical alternatives are, by definition, controversial. They challenge deeply held assumptions and are difficult to test with conventional observations. The Big Bang model is supported by a wealth of empirical evidence, from the cosmic microwave background and nucleosynthesis to the large-scale distribution of galaxies. Any new framework must not only explain Webb's early galaxies but also remain consistent with this existing body of data. Nevertheless, the very fact that these impossible galaxies exist forces cosmologists to entertain questions that would have been considered fringe just a few years ago. The emergence of these radical ideas also highlights the dynamic nature of scientific progress. Major paradigm shifts rarely occur gradually. Instead, they often arise when anomalous observations accumulate to the point where existing models can no longer accommodate them. History provides many examples, from the heliocentric model of the solar system to the theory of relativity, where observations initially seemed impossible but ultimately reshaped the foundations of science. In this context, Webb's observations could be the spark that ignites a similarly profound reassessment of cosmology. While the radical perspectives remain speculative, they serve an important purpose. They broaden the scope of inquiry. By questioning assumptions that have long been taken for granted, these theorists open the door to new ways of understanding the universe, offering potential explanations for the rapid assembly of galaxies, extreme star formation rates, and early chemical enrichment. Whether these ideas ultimately prove correct or not, they reflect a scientific community actively wrestling with evidence that refuses to fit neatly into established paradigms. This discussion naturally leads into consideration of more structured alternative cosmologies, such as steady-state or cyclical models of the universe. These theories gain renewed attention in light of Webb's findings, as they provide frameworks in which early massive galaxies are less anomalous and more consistent with the idea of a universe that is not strictly bound by a singular, linear timeline. In light of the extraordinary observations from the James Webb Space Telescope, alternative cosmological models that were once considered fringe are gaining renewed attention. Among these are the steady-state and cyclical universe theories, which offer radically different perspectives on the origin and evolution of the cosmos, especially in explaining the presence of massive, mature galaxies in what the Big Bang timeline would consider the universe's infancy. The steady-state theory, originally formulated in the mid-20th century, proposes that the universe is eternal and unchanging on large scales. Instead of beginning with a singular Big Bang, the universe has always existed, and new matter is continuously created to maintain a roughly constant density as it expands. In this framework, there is no defined beginning or first galaxies in the conventional sense. Structures like massive galaxies could exist at any epoch because the universe itself does not have a linear developmental timeline. The renewed interest in steady-state-like ideas arises from the fact that JWST has revealed galaxies that appear more evolved than the standard Big Bang model allows, suggesting that perhaps the early universe was not as constrained by time as previously thought. While classic steady-state theory fell out of favor due to evidence like the cosmic microwave background, some modern variants, sometimes called quasi-steady-state models, incorporate aspects of expansion while retaining the idea of ongoing creation or recycling, which could potentially accommodate these impossible galaxies. Cyclical or bouncing universe models offer another intriguing alternative. In these models, the universe undergoes repeated cycles of expansion and contraction, or bounces, rather than a single creation event. Each cycle could reset or modify cosmic conditions, creating opportunities for rapid structure formation in ways that the Big Bang framework does not predict. For instance, a galaxy that seems impossibly mature at 500 million years after a Big Bang might have inherited some structural characteristics or matter density from a previous cycle. In this sense, the universe's apparent youth is misleading because the matter and energy involved may have been shaped by prior epochs. Such models can, at least conceptually, accommodate early massive galaxies without requiring exotic physics within a single, linear timeline. These alternative frameworks also impact how we understand cosmic timelines like reionization or the formation of heavy elements. In a cyclic or eternal universe, periods of star formation and chemical enrichment could occur in bursts or cycles, rather than as a slow, cumulative process constrained to a singular epoch. This could explain why JWST observes galaxies that seem chemically mature and highly structured so early in the universe's conventional timeline. The very concept of too early becomes less relevant if the universe is older, or more complex, than the standard model assumes. While these alternative theories are compelling in the context of Webb's observations, they are not without challenges. Any viable model must still account for the cosmic microwave background, the observed expansion of the universe, and the relative abundances of light elements, all pillars of evidence supporting the Big Bang. However, the current tension between JWST data and standard cosmology has reopened serious discussions about whether these alternative models could offer partial or even comprehensive explanations for the anomalies observed. The resurgence of interest in steady-state and cyclic models also reflects a broader philosophical shift in cosmology. Scientists are increasingly willing to question the assumption of a single, linear beginning and consider a universe that might be eternal, self-renewing, or undergoing complex cycles. These ideas, once relegated to the margins of theoretical physics, are now part of mainstream debate because of empirical evidence that challenges the traditional narrative. The impossible galaxies revealed by Webb have acted as a catalyst, prompting cosmologists to think beyond the constraints of the Big Bang and explore models where early cosmic maturity is less of a paradox. This naturally ties into another long-standing puzzle in modern cosmology: the tension with the Hubble constant, the measure of the universe's expansion rate. Just as early massive galaxies challenge the standard timeline, discrepancies in cosmic expansion hint at deeper underlying issues with our understanding of the universe's evolution. Exploring alternative cosmologies, whether steady-state, cyclic, or other radical models, provides new ways to frame these persistent tensions. One of the most persistent puzzles in modern cosmology is the so-called Hubble tension, the disagreement over the universe's rate of expansion. The Hubble constant, denoted h_0, measures how quickly galaxies are moving away from one another, essentially providing the cosmic speedometer that charts the universe's growth. Two primary methods of measuring h_0 have consistently yielded conflicting results. Local measurements based on supernovae and Cepheid variable stars suggest a faster expansion rate, around 73 km per second per MPC, while observations of the cosmic microwave background, CMB, interpreted within the standard CDM Big Bang model, indicate a slower rate, around 67 km per second per MPC. This discrepancy has persisted despite decades of increasingly precise measurements, and JWST's discoveries are now adding a new layer of complexity to the debate. The connection arises from Webb's observations of early galaxies. These massive, mature systems challenge the standard cosmological timeline, implying that the universe formed complex structures faster than expected. If galaxies can mature this quickly, it affects how astronomers estimate distances and redshifts in the early universe. Redshift, which measures how light stretches as the universe expands, is fundamental to calculating the Hubble constant. If assumptions about early galaxy evolution or the timeline of structure formation are inaccurate, then the interpretation of redshift data, and thus the inferred expansion rate, may also be affected. Essentially, Webb's observations suggest that some of the cosmological rulers we use to measure expansion might be less straightforward than previously assumed. Moreover, the discovery of early, massive galaxies may imply that our understanding of dark energy, the mysterious force driving cosmic acceleration, needs refinement. Dark energy's influence is tied directly to the rate at which the universe expands. If structure formation in the early universe occurred more rapidly or efficiently than current models predict, it could indicate that the effects of dark energy, or its interaction with matter, are not fully accounted for in standard simulations. This could potentially help explain, or at least provide context for, why local measurements of the Hubble constant differ from those inferred from the early universe's relic radiation. JWST's data also introduces a secondary complication: star formation and chemical enrichment. The rapid assembly of stars and heavy elements in early galaxies implies that the energy output and mass distribution in these systems may differ from what current models assume. Since the light from these galaxies is used to estimate distances and infer cosmic expansion rates, any discrepancy in intrinsic brightness or mass-to-light ratios could subtly shift the derived values of h_0. In other words, the very objects Webb is observing might slightly bias the measurements that feed into the ongoing Hubble tension. The Hubble tension is not just a technical issue, it has profound implications for the Big Bang model itself. A persistent discrepancy could indicate that our understanding of the universe's early evolution, dark matter, or dark energy is incomplete. Webb's discovery of unexpectedly mature galaxies exacerbates this tension because it introduces further uncertainty into the early universe's timeline, challenging the consistency of the expansion history inferred from the CMB. If the early universe evolved faster than standard models predict, it raises the possibility that our cosmic clock may need recalibration. These findings highlight a deeper philosophical challenge in cosmology. The standard model assumes a coherent, self-consistent picture in which the timeline of cosmic expansion aligns with the growth of structure. Webb's discoveries, showing mature galaxies where only chaotic proto-galaxies were expected, suggest that there may be missing pieces in this puzzle. Resolving the Hubble tension may require not only refined measurements but also an updated theoretical framework that can accommodate both the accelerated assembly of galaxies and the discrepancies in expansion rate. It's important to note that JWST alone does not solve the Hubble tension. Rather, it amplifies the problem by providing additional empirical evidence that the early universe may have evolved differently than the Big Bang timeline predicts. This creates a double tension. Not only are early galaxies forming faster and earlier than expected, but these observations may also influence how cosmologists interpret expansion rates across cosmic time. The combination of these factors adds urgency to the debate and underscores the need for new theoretical insights or adjustments to existing models. In essence, the Hubble tension and Webb's early galaxy discoveries are two sides of the same coin. Both highlight gaps between observation and prediction. The universe appears to be more dynamic, complex, and sometimes less predictable than our standard cosmological framework allows. As with other major paradigm challenges in science, these discrepancies are prompting careful scrutiny, rigorous debate, and the search for explanations that can reconcile the tension without discarding the core successes of the Big Bang model. This naturally transitions into the broader response of the scientific community, highlighting the careful balance between curiosity, skepticism, and the willingness to revise theories in light of new evidence. How mainstream cosmologists handle these challenges offers insight into the nature of scientific progress itself. The revelations from the James Webb Space Telescope have generated excitement, but they have also been met with a measured, almost cautious response from the mainstream cosmology community. Scientists are trained to be skeptical, especially when observations appear to challenge well-established theories. The Big Bang model, despite the anomalies highlighted by JWST, has been extraordinarily successful in explaining the cosmic microwave background, the distribution of light elements, and the large-scale structure of the universe. For many cosmologists, overturning such a cornerstone of modern physics is not something to be done lightly. Instead, they prefer to scrutinize the data, test alternative explanations, and exhaust all possible adjustments to existing models before considering more radical revisions. This resistance is rooted in the scientific method itself. Paradigm-shifting claims require extraordinary evidence, and cosmology is no exception. Many researchers initially approach the impossible galaxies with skepticism, questioning whether the measurements of redshift, mass, or distance might be affected by observational biases, calibration errors, or unusual astrophysical phenomena. After all, a single outlier can always exist, but Webb has revealed multiple massive, mature galaxies across different regions of the sky, making it increasingly difficult to dismiss these observations as anomalies. Even so, the cautious approach remains dominant, reflecting a discipline that prioritizes consistency, reproducibility, and rigorous peer review over sensational conclusions. Additionally, there is a cultural aspect within cosmology that favors incremental change over revolutionary shifts. The Big Bang framework is deeply embedded in textbooks, simulations, and decades of research. Entire subfields, including studies of dark matter, dark energy, and cosmic inflation, are constructed around this model. For a scientist to propose discarding it entirely carries enormous professional risk, because the alternative must not only explain the new anomalies but also preserve the enormous body of empirical evidence that supports the Big Bang. In this environment, it is natural for many researchers to advocate first for refinements and parameter adjustments rather than radical rethinking. The cautious stance is also reflected in the way results are presented. Most papers discussing JWST's early galaxy discoveries emphasize the need for further data and careful modeling. Language like challenging expectations, requiring re-evaluation, or demanding refinements is common, while outright declarations that the Big Bang is wrong are rare. This approach underscores the scientific principle that models evolve gradually and that even dramatic anomalies must be weighed against the broader context of observational and theoretical evidence. Yet this resistance is not simply conservatism for its own sake. It is a safeguard that protects the integrity of the field. Science advances most reliably when claims are thoroughly vetted, simulations are stress-tested, and observational results are independently confirmed. In the case of JWST, this means additional observations, repeated measurements, and careful cross-checks against previous surveys, all of which are ongoing. Only after such scrutiny will the scientific community consider whether adjustments to the Big Bang paradigm, or more radical alternatives, are warranted. Interestingly, the resistance is not monolithic. Younger researchers, postdoctoral scholars, and those outside the traditional centers of cosmological research often show more openness to provocative interpretations of JWST data. They are more willing to explore radical ideas, propose alternative physics, or consider non-standard cosmological models. The interplay between cautious mainstream voices and adventurous outliers ensures that the discussion remains balanced. Data is respected, but hypotheses are tested creatively, fostering a dynamic environment where paradigm shifts, if necessary, occur deliberately rather than rashly. This cautious approach also mirrors historical patterns in science. Major paradigm shifts, from heliocentrism to relativity, were met with skepticism at first, not because they were implausible, but because the existing frameworks had explanatory power and predictive success. Only when anomalies accumulated, evidence became overwhelming, and models proved insufficient did the scientific community embrace radical revisions. The reaction to Webb's findings is following a similar trajectory. Caution first, radical revision only if incremental adjustments fail to reconcile theory with observation. Scientific resistance, therefore, should not be interpreted as denial or reluctance to change. Rather, it reflects the discipline's commitment to rigor and intellectual prudence. Cosmologists are carefully weighing Webb's evidence, testing modifications to galaxy formation models, and exploring alternative scenarios while maintaining respect for the enormous successes of the Big Bang model. This measured response ensures that any future paradigm shift is grounded in robust evidence and rigorous analysis rather than speculative leaps. The tension between resistance and the pressure to adapt naturally leads to a broader reflection on the nature of paradigm shifts in science. History shows that transformative discoveries often face skepticism before ultimately reshaping our understanding, illustrating the cautious yet self-correcting nature of scientific progress. The resistance to rethinking cosmology in light of JWST's discoveries is not unusual when viewed through the lens of history. Scientific progress has repeatedly demonstrated that transformative ideas, those that fundamentally change our understanding of the universe, almost always face strong skepticism before gaining acceptance. The pattern of initial resistance followed by gradual, evidence-driven paradigm shifts is well illustrated by several landmark examples in the history of science. One of the most famous cases is the shift from a geocentric to a heliocentric model of the solar system. For centuries, Ptolemy's Earth-centered universe was the prevailing paradigm, deeply embedded in both scientific reasoning and cultural belief. When Copernicus proposed that the Earth revolves around the Sun, his ideas were initially met with skepticism and resistance, in part because they contradicted entrenched philosophical views, but also because the observational evidence of the time seemed inadequate to fully support the claim. Later, when Galileo's telescopic observations confirmed the phases of Venus and the moons of Jupiter, the heliocentric model gained stronger empirical support, but even then, acceptance was gradual and contested. This historical example demonstrates how even correct scientific ideas must overcome deeply held expectations, incomplete data, and institutional inertia before they become widely accepted. Another striking example is Einstein's theory of relativity. At the time of its introduction, the idea that space and time are not absolute but relative, and that gravity is the curvature of space-time, was revolutionary and counterintuitive. Many physicists were initially skeptical, partly because the mathematics was complex and the predictions seemed far removed from everyday experience. The theory faced decades of scrutiny and required precise observational confirmation, such as the bending of light by the sun during the 1919 solar eclipse, before it gained widespread acceptance. Even then, some scientists continued to question or modify aspects of the theory until accumulating evidence made its correctness undeniable. The case of relativity underscores how scientific paradigms often resist abrupt overturning. Extraordinary evidence is needed to shift deeply entrenched models. These historical precedents illustrate several key features of paradigm shifts that are relevant to the current cosmological debate sparked by JWST. First, existing frameworks are rarely abandoned lightly. The Big Bang model has enormous predictive and explanatory power. It explains the cosmic microwave background, the abundance of light elements, and the large-scale structure of the universe. As a result, even when observations like the early massive galaxies or extreme star formation rates seem anomalous, the scientific community approaches them with caution, testing incremental modifications before considering wholesale revision. Second, paradigm shifts require robust, reproducible evidence. Copernicus and Galileo were not enough on their own. It took cumulative data from multiple observers and instruments to solidify the heliocentric model. Similarly, Einstein's theory of relativity required rigorous experimental confirmation to displace Newtonian mechanics. In the case of JWST, the telescope's unprecedented infrared sensitivity is providing a flood of new data, but cosmologists still demand repeated observations, cross-verification, and careful analysis before revising core assumptions about the universe's origin and evolution. Third, resistance often stems from the broader implications of a paradigm shift. Altering a foundational model changes the theoretical and practical scaffolding built upon it. In heliocentrism, the shift affected navigation, calendar calculations, and the understanding of planetary motion. In relativity, it redefined physics from the subatomic scale to the cosmic scale. In cosmology today, accepting that massive galaxies formed far earlier than predicted, or that the timeline of cosmic evolution is compressed, would impact interpretations of the Hubble constant, dark matter, dark energy, and even the mechanisms of cosmic inflation. The stakes are high, so skepticism is not only natural but necessary. History also shows that paradigm shifts are often incremental rather than instantaneous. Even revolutionary ideas are typically integrated into the broader scientific framework gradually, as evidence accumulates and theory adapts. The anomalies identified by JWST may initially prompt small adjustments to galaxy formation models, star formation efficiency estimates, or dark matter simulations. Over time, if observations continue to conflict with predictions, these incremental changes could coalesce into a more radical rethinking of cosmology, much like the way anomalies in Mercury's orbit ultimately contributed to the adoption of general relativity. Finally, paradigm shifts illuminate the self-correcting nature of science. Skepticism and resistance are not signs of stagnation. They are mechanisms that ensure that new ideas are rigorously tested and validated. Without such scrutiny, science risks embracing speculation over evidence. The current debate over JWST's impossible galaxies, early star formation, and potential cosmological implications fits neatly into this historical pattern. Extraordinary observations challenge entrenched models. The community responds with caution and incremental analysis, and only over time might a larger, more revolutionary shift occur if evidence continues to accumulate. Understanding this history helps contextualize the cautious reactions of mainstream cosmologists. They are not ignoring the evidence. They are engaging with it in the same rigorous way that scientists have historically approached paradigm-challenging discoveries. The process is deliberate, evidence-driven, and iterative, ensuring that any future redefinition of our cosmic understanding will be grounded in robust empirical support. This naturally leads into the current state of debate within the scientific community, where some researchers advocate for incremental adjustments while others increasingly explore the possibility of more fundamental revisions to cosmology. The arrival of the James Webb Space Telescope has thrown the cosmology community into a dynamic and sometimes contentious debate. On one side, there are researchers who argue that the early, massive galaxies discovered by Webb can be reconciled with the Big Bang framework through relatively minor adjustments, tweaks to galaxy formation models, refinements in star formation efficiency, or updated simulations of dark matter halo growth. On the other side, a growing number of cosmologists are considering the more radical possibility that these discoveries may indicate a fundamental flaw in our understanding of the universe's early evolution, potentially requiring a total rethink of cosmology. The tension between these perspectives is emblematic of how science handles anomalies, a careful negotiation between incremental refinement and revolutionary reinterpretation. The more conservative camp emphasizes that the Big Bang model has withstood decades of scrutiny, explaining a remarkable range of phenomena from the cosmic microwave background and large-scale structure to nucleosynthesis and the observed Hubble expansion. They argue that the impossible galaxies may appear anomalous only because simulations have underestimated the efficiency of star formation, the density of early gas inflows, or the role of feedback mechanisms. By refining these parameters and incorporating updated observations, they suggest that the standard cosmological framework could accommodate Webb's findings without discarding the underlying model. In this view, the discoveries highlight gaps in our simulations rather than fundamental flaws in cosmology itself. Yet the extraordinary nature of the observations makes this a contentious proposition. The sheer mass, maturity, and chemical enrichment of these early galaxies is difficult to reproduce in simulations, even with generous assumptions about star formation efficiency or gas accretion. Some researchers argue that we may be approaching the limits of what incremental adjustments can achieve, and that new physics, or a reconsideration of the Big Bang timeline, may ultimately be required. This line of reasoning has gained traction as additional JWST data continues to reveal a surprising abundance of massive, mature galaxies across different regions of the sky, suggesting that these are not isolated anomalies but a widespread feature of the early universe. This debate also intersects with other unresolved issues in cosmology. For instance, the Hubble tension, the disagreement over the universe's expansion rate, remains unresolved, and Webb's observations of early galaxy formation may exacerbate this problem by introducing additional uncertainties into distance and redshift measurements. Similarly, the timing of cosmic reionization is now being questioned, as these early galaxies could have reionized the universe far faster than previously thought. Each of these puzzles interacts with the others, creating a web of interrelated challenges that complicate the task of interpreting JWST data within the standard model. Social and philosophical factors also play a role in the debate. Senior cosmologists, whose careers are deeply intertwined with the Big Bang framework, tend to advocate for caution, emphasizing rigorous analysis and peer review. Younger researchers and those outside traditional academic centers are often more open to exploring radical alternatives, proposing ideas such as cyclic universes, modifications to dark matter behavior, or even more exotic cosmologies that challenge the notion of a singular Big Bang. The interplay between these perspectives ensures a vigorous and multifaceted discussion, combining empirical scrutiny with theoretical creativity. Academic forums, preprint archives, and international conferences have become arenas for these discussions, where teams present competing interpretations of Webb data and engage in detailed debates over methodology, assumptions, and implications. Some argue that it is premature to speculate beyond the standard model, while others insist that the anomalies are too significant to ignore and demand consideration of fundamentally different frameworks. In many ways, this mirrors historical scientific debates where anomalous observations forced a community to reconsider long-standing paradigms, sometimes over decades. Despite the intensity of the discussion, there is a consensus that further data is critical. JWST is still in the early stages of its mission, and upcoming observations will provide more detailed spectroscopy, deeper imaging, and larger statistical samples of early galaxies. Researchers are hopeful that this additional evidence will clarify whether these massive, mature galaxies can be reconciled with incremental model adjustments or if they will force a more radical rethinking of cosmology. In either case, the current debate exemplifies the scientific method in action: careful observation, critical scrutiny, and the willingness to revise or refine theory in response to new evidence. This ongoing debate underscores a fundamental tension in science: the balance between respect for well-established frameworks and openness to revolutionary insights. The impossible galaxies have created a unique moment in cosmology, one in which the field must decide whether the anomalies represent exceptions to the rule, gaps in our understanding, or signals of a deeper, more fundamental shift in how we comprehend the cosmos. The uncertainty and active discussion naturally lead into the next phase of consideration: what the future may hold as JWST continues its mission. Upcoming data will be critical in determining whether the early universe is as unexpectedly dynamic as current observations suggest, and whether the Big Bang timeline or even its foundational assumptions require re-evaluation. The James Webb Space Telescope has already sent shockwaves through the cosmology community, but it is only scratching the surface of its potential. With its unprecedented infrared sensitivity, high-resolution imaging, and deep-field capabilities, Webb is positioned to probe the universe in ways that were previously impossible. The discoveries of massive, mature galaxies in the first 500 million years are just the beginning, and future observations promise to either confirm these anomalies or provide clarifying context that could reshape our interpretation of the early universe. One of the most critical contributions of upcoming JWST data will be spectroscopy. By examining the light from these distant galaxies in detail, astronomers can determine their chemical composition, stellar populations, and star formation rates with remarkable precision. This will allow scientists to confirm whether the galaxies are indeed as massive and mature as current imaging suggests, or whether some observational biases or uncertainties have skewed initial interpretations. For example, precise spectroscopic redshifts will reduce uncertainties in distance measurements, which directly affect estimates of galaxy mass and age. Confirming these measurements will either solidify the impossible galaxy problem or provide a pathway for reconciliation with existing models. Another major area where future Webb observations will be transformative is statistical sampling. To date, most of the early galaxy discoveries come from a relatively small number of deep-field observations. As JWST expands its survey coverage, it will provide a larger and more representative sample of the early universe. This will allow cosmologists to determine whether these massive galaxies are rare outliers or a common feature of the first few 100 million years. If the latter is true, it would dramatically increase the pressure on the standard cosmological model, indicating that rapid, large-scale structure formation was the norm rather than an exception. Conversely, if these galaxies are found to be rare, it may suggest that current simulations merely underestimated the likelihood of occasional early massive structures. In addition, JWST's capability to peer into the infrared universe enables the study of the earliest phases of star formation and galaxy assembly. This includes detecting the faint, small galaxies that are expected to dominate the first few 100 million years after the Big Bang. Observing these smaller systems in conjunction with the massive galaxies could provide critical insight into the hierarchical growth process and clarify whether early cosmic structure formation is faster than simulations predict, or whether alternative processes are at play. Understanding the relative abundance of small versus massive galaxies will help refine theoretical models and could even suggest adjustments in our understanding of dark matter and cosmic feedback mechanisms. Webb is also poised to address the timing of cosmic reionization more definitively. By analyzing the ionization states of intergalactic hydrogen around early galaxies, astronomers can construct a more precise timeline of when and how the universe became transparent. If reionization is confirmed to occur earlier than standard models predict, it will reinforce the idea that the early universe was highly efficient at forming stars and galaxies, lending weight to the challenge posed by massive early galaxies. Conversely, if reionization is found to align more closely with prior expectations, it may suggest that the earliest massive galaxies were isolated anomalies rather than evidence of a fundamentally accelerated cosmic evolution. Future JWST data will also shed light on the Hubble tension. By providing improved distance measurements to high redshift galaxies and refining redshift estimates, Webb can help constrain the universe's expansion rate with greater precision. This will contribute to resolving, or potentially exacerbating, the ongoing debate over the Hubble constant, offering a more detailed picture of whether the early universe's expansion history is consistent with the standard model or indicative of new physics. Finally, Webb's ongoing mission will likely reveal entirely new surprises. Every time astronomers have pushed observational boundaries, from Hubble to ground-based telescopes, unexpected discoveries have reshaped our understanding of the cosmos. Webb's ability to see farther, deeper, and in unprecedented detail makes it highly probable that additional anomalies, unpredicted phenomena, or entirely new classes of galaxies will emerge, each with the potential to further challenge existing paradigms. The telescope's long-term surveys, time-domain observations, and spectroscopic follow-ups will ensure a continuous stream of data capable of refining or revolutionizing our cosmological theories. In short, JWST is only beginning to rewrite the story of the early universe. While the first discoveries have already posed profound questions, the full scope of Webb's capabilities promises a sustained period of investigation, debate, and potential transformation. Upcoming observations may confirm that the early universe was a surprisingly efficient, rapid, and complex place, or they may reveal subtleties that allow the standard Big Bang framework to accommodate these seemingly anomalous findings. Either way, the telescope is setting the stage for a dramatic re-evaluation of cosmic history and the mechanisms that shaped the universe in its first few 100 million years. This anticipation naturally leads into the broader implications of JWST's discoveries for our understanding of the universe, including how they force us to confront long-standing assumptions and challenge our perception of cosmic history. The James Webb Space Telescope has already reshaped our understanding of the universe in ways that few instruments before it have. Whether or not the Big Bang model ultimately survives the scrutiny prompted by JWST's discoveries, one fact is undeniable: our perception of the early cosmos has been transformed. The telescope has revealed a universe that is far more complex, dynamic, and rapid in its formation than previously imagined. Massive, mature galaxies appearing just hundreds of millions of years after the supposed beginning challenge long-held assumptions about cosmic timelines, star formation, and structure growth. These revelations compel scientists and the public alike to reconsider what we thought we knew about the origins and evolution of everything around us. Even if the Big Bang framework ultimately proves robust, perhaps with minor adjustments to account for rapid star formation or accelerated galaxy growth, JWST has already forced us to confront the limits of our knowledge. It has revealed that the early universe was capable of producing extraordinary complexity in ways that simulations had not predicted. Observations of early galaxies, reionization processes, and chemical enrichment have opened entirely new questions, suggesting that our current models, while powerful, may only tell part of the story. The telescope's ability to peer into the infancy of the cosmos has effectively pulled back a curtain on an era that, until now, existed largely in theory, giving humanity its first direct glimpse of the formative processes that shaped the universe. Moreover, JWST's discoveries exemplify the self-correcting, exploratory nature of science. The telescope has not merely confirmed what we thought we knew, it has challenged assumptions, provoked debate, and stimulated a re-evaluation of theoretical frameworks. Scientists are now actively considering a spectrum of possibilities, from incremental refinements to galaxy formation models, to radical alternative cosmologies such as cyclic universes or modifications to dark matter physics. In doing so, JWST is fostering a period of intellectual tension and creativity that is the hallmark of major scientific revolutions. Just as historical discoveries like heliocentrism, relativity, and quantum mechanics required a fundamental rethinking of previously held assumptions, Webb's early findings may serve as the catalyst for a similar transformation in cosmology. The telescope also underscores a profound philosophical lesson: the universe often defies our expectations. The discovery of galaxies that seemingly should not exist reminds us that even our most cherished models are provisional, subject to refinement and revision in the face of new evidence. JWST is a testament to humanity's curiosity and ingenuity, providing tools capable of exploring questions that have long been beyond reach. Its findings invite us to embrace uncertainty, to marvel at the universe's complexity, and to recognize that our understanding of cosmic history is still incomplete, no matter how confident we might have felt before. In practical terms, the impact of Webb's discoveries will resonate for decades. Upcoming data will clarify the nature of early galaxy formation, refine our understanding of the Hubble constant, illuminate the timing of cosmic reionization, and possibly reveal phenomena that we cannot yet imagine. Each new observation will either reinforce the Big Bang paradigm, challenge it, or, perhaps most intriguingly, suggest a synthesis of old and new ideas that reshapes our fundamental conception of the cosmos. In this sense, the telescope is not only an observational tool but a catalyst for theoretical innovation, driving cosmology toward a deeper, more nuanced understanding of the universe's origin, structure, and evolution. Ultimately, whether the Big Bang survives in its current form or gives way to new models, JWST has already achieved something remarkable. It has expanded the boundaries of human knowledge, confronted scientists with unanticipated complexity, and inspired a profound re-evaluation of the universe's earliest epochs. The cosmos, as revealed through Webb's eyes, is far richer, stranger, and more beautiful than our models had anticipated. In forcing us to question our deepest assumptions, JWST embodies the very spirit of exploration and inquiry that defines science itself. It reminds us that the universe is not a static backdrop for human observation. It is an ever-evolving, enigmatic, and astonishing reality, waiting to be understood. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.